Hello, a pleasant day to you. I am Sherlyn Aldoza, and I'd like to use this short video to introduce to you the concept of system dynamics. Now, to understand system dynamics, first we must understand what is a system. A system is any entity that are made of parts which interact, and together these parts creates a certain whole. According to Meadows, a system is a set of elements or parts that is coherently organized and interconnected in a pattern or structure that produces a characteristic set of behaviors, often classified as its function or purpose. Many things or us can become a part of a system, may it be a natural system or a man-made system. We should also understand that for every system, you have the so-called boundary. The system boundary is a conceptual line that divides a system that you want to understand from everything else. Okay? It's very useful to think that for every system, okay, there is this certain scope or limits, and you need to understand what are those that are part of this scope that affects your system's performance. Okay. Now, the way to structure a system is first to identify what belongs to the system and what is not, okay, which is very critical. You need to think well, what are those, okay, that belongs and what are those that are not, and you need to identify what are the inputs and outputs and the internal dynamics of your system. Knowing the system, a system may fail because it fails to achieve its purpose. Maybe the parts are poorly designed, okay, or poorly connected, or it is not, of course, because of external shock. It is inherently incapable of meeting its purpose, or it attempts to adjust to changes, or maybe the policies are badly designed. Okay, it is important to study this system dynamics so that in the future you will be able to address this system failure. Okay. And in order to address such system failure, we must also understand what is systems thinking. So systems thinking is just like in this picture. Okay. There are 6 blind men and an elephant. This is a parable from India in which these 6 blind men will be able to identify the object, or say for example this an animal in front of them if they will touch them. Okay, but each of them are assigned to the different part of this elephant. Okay, this one man touched the tusks and found out that it was like a spear, so he thought that the elephant was like a spear. This one thought that the elephant was like a snake by touching the trunk. This one also thought that the elephant was like a tree by touching the legs. This one thought that the elephant was like a wall by touching its body. This one thought that the elephant was like a rope by touching the tail. And this one thought that the elephant was like a fan by touching those ears. So they had these different views. They had different findings. Okay, they were arguing what an elephant really is because they had different views. And how do they find out that it was an elephant? Well, okay, they collaborated. Their collective wisdom, okay, they collected their ideas and combined them, and they were able to identify, okay, that this is what an elephant would look like. So according to Meadows, the behavior of a system cannot be known just by knowing the elements of the system. Okay, this is what systems thinking is trying to convey. Systems thinking is an ability to see things as a whole, or the holistic view. A systems thinker, okay, in the future, you should not limit your thinking to what's the things that you have seen. You should look at it deeper, okay? You should look at the holistic view. Now, the history of systems dynamics or the systems thinking originated in 1956 when the System Dynamics Group was created by Professor J.W. Forrester at the Sloan School of Management at Massachusetts Institute of Technology. He was an electrical engineer who invented the random access magnetic core memory in digital computers, and he used a system dynamics methodology, okay, that was based on ideas of feedback, such as encountered in electrical and mechanical control systems. He applied his background in computer sciences and engineering to the development of computer modeling and analysis of social systems. Forrester's experience as a manager in the General Electric Company led him to conclude that the biggest impediment to progress comes not from the engineering side of industrial problems, but from the management side. Okay, this was because he finds some difficulties, okay, as well as his fellow corporate managers. He reasoned that, okay, the social system is much more hard to understand and control compared to the physical system. And then system dynamics evolved from that time. So what is system dynamics then? System dynamics is an approach to understanding the nonlinear behavior of complex systems over time using stocks, flows, internal feedback loops, table functions, and time delays. System dynamics is also the use of models for the design of improved organizational form and guiding policy. Okay. Now, this is the characteristic of a complex system that system dynamics wants to solve. It is tightly coupled, okay? It's like this domino effect that everything influences everything else, okay? You can't just do one thing. That one thing may impact the entire system or the entire organization, okay? It's tightly coupled. Then it is dynamic. When you say dynamic, many changes will occur at any time scales. We know that change is only constant thing in this world, and a certain system must be able to adjust to those changes. Next, it is policy resistant. Okay, we say policy resistant. There are many obvious solutions to problems that fail, okay, or may actually worsen the situation. A complex system is counterintuitive. Okay? The cause and effect are distant in time and space. And also it exhibits trade-offs. Okay? The long-term behavior is often different from the short-term behavior. We must understand that these characteristics of complex systems, okay, so that we may be able to properly define the system that we want to address. Now, these are the primary elements of systems dynamics. We have the feedback, the accumulation of flows into stocks, and the time delays. This is a simple map or structure of a system, okay, which shows the feedback, accumulation of flows into stocks, and these time delays. Say, for example, in the student population. A student population can be our stock, okay? Because this is an accumulation of student enrollment, okay, and a decrease in student graduation. Now, we say feedback. If we have student enrollment, or if we have an increase in students enrolled, it will lead to increase in student population. Now, this increase in student population also feedbacks to this initial student enrollment, okay, Because when student population increases, more students will be enrolled in the future. Now, these red lines here represents the delay, which means that it would take time for the students to be enrolled again for the next year. Now, if more students are there, okay, more will graduate also in the future. And it would take time, this delay, okay, it would take time for the students to graduate, like it would take them 4 years, 5 years to graduate. Now, if we have more more graduation, okay, this will lead to a decrease in student population. Okay, it feedbacks to student population. So this is just a simple example of a simple system archetype in which it included these primary elements of the system. And when you do one, okay, later on in the future, you must understand what are those elements which feedbacks with another element, okay, what are those accumulations and which has those delays, okay? Now, this is the system dynamics perspective, okay? The system dynamics perspective tries to get underneath the events. No? There are instances that we easily react and respond to events that are visible. Okay, that's what is currently happening. Okay, what's the trend? Trending karon, no? What are those events? We tend to react and respond to those. Now, the system's perspective tries to go down deeper. Should ask what's been happening. Where are there changes, the contrasts, and continuities? That when you go down, there are those visible ones, those rarely seen that affects these events. So these are the patterns and trends, okay, that is behind those events. We should understand these patterns and trends so that we could anticipate, plan, and prepare for the future, for the recurring of the events. And when you go down deeper in this pattern and trends, we can see that there is a certain structure, including the mental model that's behind it, that's behind them. Okay, we should ask why and how. What would explain those patterns and trends? What is the thinking and what is its impact? And when we understand this, okay, you would know the design, okay, how to design, create, and transform, okay, this structure in order that these patterns and trends, okay, may be changed or maybe be addressed, okay. We may be able to plan ready so that in the future these events will happen positively, will lead to a positive impact, okay, to our system. As we move our perspective from the event level to the structural level, we have a better understanding of what is really going on in the system. Okay. Now the systems mode, the system archetypes, okay, are some of the essential things that you must know in system dynamics modeling. These system archetypes are patterns of behavior of a system. Systems expressed by circles of causality have therefore similar structure. Identifying a system archetype and finding the leverage enables efficient changes in a system. Okay? These are simple archetypes, okay, or basic structure of the system. That for every system, okay, it is composed of a feedback loops. Okay? Remember the primary elements, we have the feedback, the accumulation, and the time delays. So it simply means that for every action, it leads to some kind of results. which further shapes future actions. Okay, this is the circles of causality. This is what system archetypes is trying to convey. Okay, and we must understand the system archetype of the system that we want to study. The system dynamic modeling process is this. Most system dynamics models are created following these 4 stages. We have conceptualization, formulation, test, and execution. Now, if you will make a model from that, okay, I chose this model adapted from the methodology of 5 languages, okay, to model a system dynamic adapted from Andrade. Okay. Here is a methodology. For every phenomenon or event that happened, we should understand the mental model, okay, or the paradigm that governs it. That this paradigm of system dynamics model starts from system verbalization. From the physical system that we observe, okay, we can create a causal loop diagram. We can create a simple map of the system, okay, a map of the structure of that system. What are those elements or what are those parts of that system that interacts with each other? Then from the causal loop diagram, we will transform that one into a stack and flow diagram, okay, so that we would know what are the inflows and outflows and what are those stocks, okay, from that system. And from that stack and flow diagram, those parts, those elements can be calculated, okay, through these mathematical equations. Okay. Through these mathematical equations, you would know what are those rates of changes, what are those integration of the flow inflows and outflows, okay, from our stack and flow diagrams. Then from that, we can do now the model simulations. Here, this is an iterative process because here we can model the behavior of our system over time, over the coming, over the months or coming years, okay? So that we could develop policies or model scenarios that may impact our system, okay? We can choose what are those policies that we must develop, okay, in the future so that it would attain the goal or the objectives of that certain system. So that is the system dynamics methodology. So from that system dynamics methodology, there are 2 important tools that we must do in modeling our system dynamics problem. First, we have our causal loop diagrams. Okay, the causal loop diagram is a simple map of a system with all its constituent components and their interactions. Okay, this is a simple map. This is a model of our system which details our system qualitatively. Okay? It determines the elements or parts of the system that influences one another and also shows the interactions of those elements. Okay, this is the overall or how we see the system. Okay, system concept as a whole. Then from this concept, from this CLD, we can then create a stack and flow diagram. Okay, this is a more concise structure, a more concise map from the CLD, and we can add more parts, more variables in this system, and we can measure them quantitatively this time. The stack and flow diagram depicts the structural understanding of a system the causal structures that produces the observed behavior. Through this, we could identify what are those inflows, okay, coming in our stocks, and what are those outflows coming out from our stock. And through this, okay, through some powerful softwares, okay, we can then simulate, okay, what if there are changes in our inflows, what will happen to our stocks? Okay? If there are increase in our outflows or decrease in our outflows, what will happen to our stock? Okay. Through this, we could we could simulate the behavior of our system over time. If there will be changes that will occur in this, and we could develop policies. Okay? We can become ready to any scenario that may happen in the future. So system dynamics modeling and simulation can be used to compute how system would react upon certain inputs. So it's an iterative process. We can do trial and errors here. We can do run, test, run, and test again, so that we may come up, or we may choose what are those policies that will address our scenarios well, okay, in the future. And it will help a certain system, a certain organization achieve their goals and objectives for the success of that certain organization, for that certain policy, for that certain system. And so on my next videos, I have some video tutorials for the causal loop diagram and stack and flow diagram by using this system dynamics software, which is Stella, and I think from the High Performance Systems Incorporated. I will be also using Ventem from Ventana Softwares, from the Ventana Systems Incorporated, I mean. Okay. So later on, we will be able to know how to model a certain system. You can read more from these references. Okay. That will be all for my presentation. Thank you so much for listening. Have a great day.